Okay, let's solve this second order linear DE using power series. We could solve it using Laplace transforms, or honestly, it's really not even hard. Move this y to the other side, we get second derivative equals negative the original function. We know the general solution to that, sines and cosines. We've solved that a couple of times, but it's a good one to do using power series. So our p of x here in front is 1. That has no singularities. There's no place where that equals 0. We won't have any singular points here. So we're going to expand this about the point x equals 0. So I'm going to build the power series at x equals 0. We assume our solution looks like this. Then take two derivatives. You should check this on your own that this is what you get if you take two derivatives. Now note, we won't always play this game here, but in this case it will help. The first term, when I plug in n equals 0, this whole thing is 0. The second term, n equals 1, makes this 0. So the first terms are 0. I might as well start counting at 2. That's the first non-zero term. That's going to be helpful in a minute. So I plug this in for y double prime. I plug the assumption here in for y, and I get this equation. This can only be true if first we want to combine together our like powers of x. I want all the x cubes from here matched up with x cubes from here. X to the 12ths here, matched up here, and so forth. So the easy way to do that is make them look the same. Force this to look like x to the n and force them to start at the same point. So the simple way to do that, if I need this to go up by 2, I make everything here inside the sum go up by 2, and I counteract that by making this go down by 2. Whatever I do inside here, I undo by doing the opposite here. That's the shortcut. This goes up by 2, up by 2, up by 2, down by 2. The long way to do that is rename k equals whatever we have here so that these two will look the same. So this will be a k. That means n equals k plus 2, and rewrite all these in terms of k. So when n equals 2, k would be 0. N is k plus 2, n is k plus 2. N minus 1 would be k plus 1. N minus 2 would be k. Now look that they match up. I've got x to the blank, x to the blank. They both start at 0. The choice of what letter I use for my index is arbitrary. I could call these both k's or both n's. So now I'm going to rename. I know this looks weird, but I just said k is n minus 2. Now I'm going to replace k's with n's. And I know that sounds weird. It sounds like we're kind of backtracking, but we're not. It's okay. We're allowed to do this. So now I'm going to replace all these k's with n's. So again, the shortcut here to get from here to here is I need these powers to match up. So I need these, all of these, everything inside the sum to go up by 2 to match here just regular n. The way we counterbalance that is bring this down by 2. Okay, now my sums start at the same place. I have the same power. I can combine them together into one single sum. So I've just written an plus, I wrote it in the other order, but it's just everything times x to the n. The only way a polynomial, even an infinite polynomial, can equal 0 for every possible value of x is if every coefficient equals 0. So that means all of these things here must equal 0. So let's just write that down. And we solve this. I always want to solve it for the bigger one. So solve for an plus 2 in terms of an. So just move the an to the other side, divide. And that's our main goal. That's what we're going through all this work for, is to find this recursive formula. So that's what we're always after, is our recursive formula. And remember, we're always going to have the degree of the, or the order of the DE tells us how many free variables we'll have. This is second order, so I'll have 2 free variables. That's the same thing as saying I would need 2 initial values. So the first 2 variables, first 2 coefficients will be free. A0 and A1 are free. Everything is going to depend on them, and notice that each term, each coefficient, depends on 1, 2 behind it. That's pretty common. That won't always happen, but that's pretty common. So let's start plugging in values of n here. So I'm going to use this formula and try to notice a pattern for my A7, A8, A9, and so forth. So if I plug in n equals 0, try this on your own. In all of these, use this formula. A0, I get this expression. Plug in n equals 1 on both sides. I get this. Plug in n equals 2, and I get this. But I already know A2. A2 was right here. Everything is going to depend on A0 and A1. So we're always going to keep going backwards and backwards until we find it in terms of A0 or A1. Here's A4. Notice that's 4 factorial. That was 3 factorial, 2 factorial. Plug in an n equals 3. We get A5 is this. That gets us back to A1 because A3 was this. That's a 5 factorial. So note all the ANs will have an A0 or an A1. And notice here the evens go back to A0, the odds go back to A1. Notice that we're alternating signs. So like A2 is a negative A0, but A4 is a positive A0. A3 was a negative A1, but A5 is a positive A1. So we could just write out, if we wanted to, if we were trying to say, write down the first 5 terms, then we would just say y equals and go all the way up to the x to the 5th. But we're going to separate this out into a y1 and a y2. The y1 is the one that has all the a-naughts in it. The y2 will have all the a1s in it. So we notice a pattern here. The a-naughts are in the evens. The a1s are in the odds. So y1, technically this is y1 here without the a-naught. Will look like this. Remember, you're always going to have an a-naught in every one of these. That's our first term. And then all the even powers. Notice they're alternating signs. These are what I got up here, and I just noticed a pattern. The y2 is this stuff here in the brackets. That was all the odd powers, and we were alternating signs. You can look these up. These are the Taylor series expansion, technically the Maclaurin series expansions, of cosine and sine. So y1, technically, y1 was just cosine, and y is a0 y1 plus a1 y2. So there's our solution. Our solution is the sum of these two. Our solution is y equals y1 a0 y1 plus a1 y2.